you, Daniel, for introducing me. Doing my work in my PhD, I'm working on solving problems related to design space exploration for instruction set architectures, especially RISC-V. Here in this figure, you can see on the right side the steps which are involved in exploring and evaluating custom instructions for RISC-V. Of course, we start with the actual programs and benchmarks we are interested in. Then we need a compiler and linker to finally evaluate the usefulness of our instruction set on a simulator. Then, based on this, this evaluation, and maybe and often also using a profiling tool, we can then propose new custom instructions which can be added to the instruction set. On the left side, you can see that there is an ISA model for the RISC-V ISA, and while the steps on the right side of this figure are already very well established, there are two steps on the left side, the proposal of custom instructions and the integration of custom instructions, which currently need a lot of manual efforts. Especially the integration of custom instructions into programs and benchmarks is currently very important because, of course, we want to make use of our custom instructions that we have just added to the RISC-V ISA. This presentation will be about eliminating this step and instead introducing compiler-level retargeting. And this retargeting can, of course, also be done manually, as explained in Alex's tutorial on Monday for LLVM. But, of course, for making this iterative procedure of ISA extension design space exploration, of course, this needs to be fully automated. Now, I would like to discuss RISC-V modeling formats. When describing the RISC-V ISA or in any other ISA, you typically have to model the encoding, the assembly format, as well as the actual semantics and behavior of the functions. There are some proprietary ISA models like Codel and NML, but there are also open source ones like Sail, which is used as a golden reference model for RISC-V extensions, but also CoreDSL, which will be used in this talk. There is always also existing work in terms of retargetable software compilers, both from the commercial side, from CodaSip and Synopsys and a few others, but there are also academic works on this field, and some of them are even open source. We are introducing CL5, which is a tool for our semi-automated LLVM support for RISC-V ISA extensions, including support for autovectorization. The input of our tool is the CoreDSL description, like shown here on the right, and the output of our tool is a patched LLVM toolchain. The flow can be seen here in this figure, but today I would like to focus on the most interesting part, which is the pattern extraction and the code generation aspects. Before I talk about our approach, I would like to introduce the different levels of retargeting support which exist in the which can be added for LLVM. The first level is assembler level support, and you almost likely need to implement that to make use of new instructions. As shown here, if you only have assembler level support, software developers need to sit down and handwrite assembly statements to make use of any added custom instructions, which is, of course, not a very good idea and should be avoided because writing assembly is quite error-prone and needs a lot of efforts. An alternative would be implementing support for intrinsics and built-ins, which allow the software developers to make use of custom instructions, like, for example, a multiply and accumulate instruction from high-level languages such as C and C++. However, while now the functions can be added or invoked using simple function calls, they still need to be added manually by the software developers. This can be solved by also adding code generation support in the compiler. Here, then the compiler can make use of so-called code generation patterns, which I will introduce later, to automatically detect opportunities for adding instructions supported by the targeted ISA In this example, the software developers just need to write, for example, accumulator plus equals x times y, and it's the job of the compiler to figure out, okay, we can add this custom Mac instruction. You could even go one step further and also support our code generation for SIMD type instructions. And then we could also automatically detect this vectorized loop and use proper SIMD instructions if available on the target. Now, before introducing our approach, I would like to introduce why instruction selection patterns are important and how they are used. On the right side of this flow, of this figure, you can see how a regular C or C++ program is compiled using LLVM. We start with the Clang front end, which parses the C or C++ code and translates it into LLVM IR, which is LLVM's intermediate representation. Then LLVM applies a lot of well-established optimizations on the LLVM IR functions before lowering the LLVM IR to a so-called selection deck. And based on this selection deck, there's a next step being applied called instruction selection. And this is where generic generic LLVM instructions are translated into target-specific machine instructions. To make this instruction selection happen, LLVM relies on so-called instruction selection patterns, which usually have to be manually provided by LLVM's backend developers. Our approach tries to eliminate that by the steps which are now shown on the left. We start with the behavioral functions of, or the behavioral code of the instructions in the core DSL syntax, and we implemented a custom CL5 frontend for translating the behavioral code into equivalent LLVMR functions. This was quite easy to do because core DSL uses a syntax which is very similar to the C language. Now, since we have our behavioral or instruction behavior as LLVM IR functions, we can apply exactly the same optimizations as LLVM would apply on a conventional program. Then, when we also come up with the selection deck of our instructions, then we are making use of a hook which can emit the deck and finally translate the deck into the instruction selection patterns, which can be written out in the table gen syntax. The advantages of this approach are that we use a lot of existing infrastructure in LLVM, aka we do not really need to reinvent the wheel implementing optimizations which are already quite established in LLVM for many years. And since we do the same optimizations on both branches here, we have an increased likeliness that the instructions that we are, or that the patterns that we are generating for the instructions will actually match with the decks which occur in real-world programs. And finally, by making use of LLVM and making use of all the optimization passes, SIMD instructions can also be detected automatically, and we can generate also SIMD patterns, even if core DSL has no notion of vectors at all. For evaluating our CL5 tool, we first took the core V extension, which is developed by the Open Hardware Group and consists of over 300 more like general purpose instructions, and it's also implemented on the CV32A40P core. For our comparison, we came up with 4 different configurations. One is a baseline RISC-V target without any vendor extensions, using upstream LLVM, and the other, the reference target is the core V reference LLVM, which was of course implemented manually by the community of the Open Hardware Group. Then we have 2 more configurations, which are generated by CL5. One is this LLVM without SIMD support, and the other one is the LLVM with SIMD support. And by having a look at the top 2 figures of the evaluation, you can hopefully see that for the non-SIMD case, the relative runtime improvements that we can see for our generated LLVM toolchain basically match with the expected runtime improvement that you can achieve using the manually implemented reference LLVM. For the SIMD case, I have to mention that SIMD code generation support was not added to the manually implemented reference LLVM now. So, but with CL5, we can actually also make use of the SIMD instructions, which leads to very good performance improvements, like up to a factor of 8 for some benchmarks, which are vectorizable very well. Then we wanted to see if our CL5 approach also generalizes for more complex instructions apart from the core V instructions which we have used first. For this, we took a simple 32-bit rotation instruction from the RISC-V bit manipulation extension and some special SHA-256 hashing instructions from the RISC-V scalar cryptography extension. And after implementing them in the core-DSL syntax, we saw that CL5 can be used effortlessly to generate the LLVM support for these instructions, including code generation. And that's how we can achieve these speed-ups for the rotation and for the more specialized instruction on the nettle SHH benchmark. Before I conclude my talk, I would like to talk about the recent developments in the CL5 project. We have migrated to global ISAL this year because that's an alternative to the selection deck and will eventually be used quite a lot in the future in LLVM. And we have just added support for custom instructions, 64-bit targets and custom registers. Right now, we are looking into also automating the generation of test cases for the compiler, like smoke tests and unit tests. And we are also looking into generating support for register pairs, which will hopefully allow us to generate the LLVM support for the RISC-V packed extension when it's being finalized in the future. Later, we will also be looking into supporting more data types like floating point and custom integer data types, as well as, for example, microarchitectural array scheduling. In my talk, I have explained that the exploration of custom ISA extensions is a highly complex iterative process, and especially automated retargeting is essential to eliminate all manual efforts. I have introduced CL5, which is a retargeting LLVM compiler for RISC-V, that is using a novel approach for robust pattern generation and SIMD support. I compared CL5 with the reference core V vendor toolchain and also demonstrated the usability with the custom hashing instructions. That finalizes my talk. I also have a poster up tomorrow, so I'm happy to answer any questions. And you can, since CL5 is open source, you can also try it out on GitHub.